Okay, so I'll start. So what I plan to do in these, I have four, we have 4 2-hour slots. I do it and then Marina takes over. But what I want to try and do is give you the basic principles and mathematics of what you need for solid state NMR. Actually, it's pretty fundamental stuff, so you actually need that for understanding many different forms of NMR as well. I'll concentrate mainly on solid state NMR. Morning. I wanted to give you some handouts, but actually the system with the printing has changed, so I couldn't actually manage to print anything. I'll try and get something printed for the next time. Those of you who like handouts, but do take notes anyway, because probably I'll deviate anyway from what I prepared. Okay, so what I wanted to start with is assuming that we want to understand NMR, in particular solid state NMR, and one of the things we have to do is turn these lights. I don't want to turn the lights up at the front here. The light switches anymore? Okay. Is the light switches set? Okay, I don't know. So what we need to do is understand how the nuclear spins interact with their environment and how to write that down in a quantum mechanical way, in such a way that we can do some theory and understand how things work. That's the first step. So in this chart here, I've divided up the terms which are relevant to NMR in actually in diamagnetic materials. That means without any unpaired electrons. So there's another branch of NMR to do with materials like metals and paramagnetic solids, where there's a few more terms as well. But let's ignore those for the time being, so this will be like an ordinary material. So what's going on here is that we have molecules which have nuclei in them. And the nuclei are surrounded by electrons. That's what holds the molecule together. And then we have a magnetic field as well. A large static magnetic field, we call that B0. And these nuclear spins can interact with the electrons, they can interact with the field. So for example, there's a direct interaction between a nucleus, each nuclear spin, and the magnetic field. So call that number 1. What's the name of that interaction between the nucleus and the magnetic field? Does anyone know? No? Zeeman interaction, yeah. So this is the big one. Normally in NMR, then one tries to make this interaction as large as possible by using the strongest possible magnetic field. In fact, it doesn't appear on this diagram. I should really have had, when I think about it, I should have had another branch here saying Zeeman interaction. So that doesn't really involve the molecule. It's the same for every nucleus of the same type, like protons, interacts with the external magnetic field in the same way as the Zeeman interaction. Okay, then we can have an interaction of the nuclei with each other. We could call that number 2. And Anyone know what that's called? Yeah? Yeah. Dipole. Yeah. Yeah. That's the direct dipole-dipole interaction. And that's a small interaction, so make it. Okay, then there's another interaction which involves nuclear spins interacting with the electrons, which then interact with another nuclear spin. Call that number 3. Any name for that? Anyone? Other than Richard? J coupling, yeah, that's right. That poor interaction doesn't really have a name except the term in the letter used in an equation of the people who first discovered it, which just happened to be J, so it's become known as the J coupling. And that's actually a very small interaction usually. And then we have an interaction from the nuclei to the electrons, and then from the electrons to the magnetic field. That's number 4. What's that called? That's called chemical shift. Very good. And roughly speaking, that's about the same size as the dipole-dipole interaction. And we have one more as well. Which is the nucleus can interact with the electrons around the nucleus. And what's that called? Yeah, that's the quadrupole, at least the quadrupole interaction is the main part of it. And that's actually quite a big interaction, except when the spin is 1/2, in which case it vanishes. So this is our landscape of the NMR interactions. Yeah?
There's a quadrupole interaction, it's object interaction.
Does it what, sorry?
Quadrupole interaction, it's object interaction. With electron interaction or object with.
Sorry, I'm not.
Quadrupole interaction. You know, with the electron, with a nucleus, electron or a nucleus object with.
The nucleus with?
Yeah, the orbits. Because you've got few objects with different size.
Yeah.
Electron.
Yeah, you know, the electrons can be in different orbitals, they can have different spins, all sorts of things, but yeah, these are unpaired paired electrons, so no electron spin. So the nucleus can interact with the electrons in the environment, and that's usually called electric quadrupole interaction. Are you okay with it? Yeah. So here I've divided it up in a slightly different way between electric interactions and magnetic interactions. So the electric one is the quadrupole interaction, quadrupole coupling. That's the only one which involves the interaction of the nucleus with electric fields in the vicinity of the nucleus. So that's electric. And all the others are magnetic.
What about the decoupling and chemical shift? Also interact with the electron.
They do, but through as a magnetic interaction. So, for example, the well, we'll look at the chemical shift in a minute, but the electrons can start to have currents in the electrons induced by the magnetic field. And then those currents generate small extramagnetic fields, and then they interact with the magnetic moment of the nucleus. So we see already in this diagram the quadrupole nuclei, so we call nuclei with spin larger than 1/2, which are actually the majority in the periodic table, are called quadrupolar nuclei. And they have this large quadrupole interaction, which is actually much larger usually than all the other ones, except for the Zeeman interaction. So they're always a bit special, and we're going to put those to the side for the most part now, and talk mainly about spins 1/2, which only see these 4 interactions. Okay? Yeah?
And do you put the night shift, the chemical shift as well, or?
So that's metals, and that's for
Sorry.
materials which have unpaired electron. Includes metals. But yes, you would, if you would put it anywhere here, you would put it together with the, say in metals there's another, something which looks very much like a chemical shift, but in metals it's called night shift. It's interaction of nuclei with the conduction electrons, the ones which carry the electrical current in the metal. But it actually involves electron spin, so it doesn't really quite belong in this diagram. Okay, so that's our landscape. Okay with that? Yeah, and the next few slides here, which you'll get in the handouts, essentially go through those diagrams which I just sketched here. So the chemical shift involving the field, the electrons, the nucleus, the direct dipole-dipole coupling, direct interaction between the magnetic moments of neighboring nuclei, the J coupling, which involves the electrons, the quadrupole coupling, which involves an interaction of the electric charge distribution inside the nucleus with the electrons. And that only occurs if you have spin larger than 1/2. Yeah, so that's the sketch of the nuclear interactions. Now, actually, I think I'm going to deviate from my maybe. I want to turn this off. Well, never mind, I'll use it over here. Now, each of these terms can be written and is written as a Hamiltonian. In quantum mechanics, the Hamiltonian operator contains all of the terms for the different nuclear interactions. This would be the spin Hamiltonian. Which is the one which governs how the nuclei behave in the presence of the magnetic fields and all the interactions they see. So for each of these terms we need to write down an interaction. And actually each of these interactions has a form as follows. So if we look if you look number one at the Zeeman interaction, we would write it like this. Okay, what does this mean? Let's just unpack this. So the gamma here, this is called the magneto-gyric ratio. And this simply says how magnetic a nucleus is. So the larger the gamma value, the more magnetic it is and the more strongly it interacts with the magnetic field. So that's different for every type of nucleus. Now this term is a product of the spin operator for nucleus number J. I've written it as a vector, so that actually you can think of as being a set of angular momentum operators arranged in a row. And then B is a vector, the magnetic field. And at this point, it's actually good here not to assume anything about the magnetic field. Very often we assume the magnetic field is along the z-axis, but it's quite good to write these equations generally. So at the moment I'm not assuming anything about the direction of the magnetic field. So we have the dot product of two vectors. So ij dot b just means multiply this by this row vector by this column vector. So we have ix, ijx, bx plus ijy, by plus ijz. Bz. So these are the angular momentum operators. Is everyone comfortable with that? Yeah? So that's the Zeeman interaction. And we can write all of the interactions in a similar way. So we can write down the direct dipole-dipole interaction. Between two spins J and K. So we're talking about, we have a nucleus J and a nucleus K. And we want to write down the interaction between the two nuclei, and that's done in a similar way. So we have the components of the angular momentum operators for spin J, Ijx, Ikx, Iky. Right, is a row vector. And we have this thing in the middle. And then sorry, I made a mistake here. Ijy, Ijz, Ikx, Iky, Ikz. And then we have here a matrix in between. And that's called the dipole-dipole coupling tensor. tensor is a way of coupling together two vectors. And the theory of NMR is full of these objects called tensors. Why is this type of thing called a tensor? The name actually is quite illuminating. It comes from classical mechanics. If you have a material and you apply a stress to it, which basically is pressure, and the material distorts. Basically it moves, and that's called strain. Now if the material is, so if it's an ordinary liquid, then if you apply a stress, like pressure, then it compresses, but it compresses always in the same direction as the stress you're applying. So basically if you I can never see these erasers. Anyone see that? No? So if you have a liquid, then it basically shrinks in the same direction as the stress which is being applied. But for some materials, so suppose you have a block of wood, but the grain is sort of done diagonally like that. Then if you apply the stress like this, then it may actually distort in a funny way. That's probably not exactly how it works, but anyway. The anisotropy of the material causes the distortion to be in a different direction to the stress which is applied. So you basically always have like strain is a tensor times the stress. But this can be a vector and this can be a vector. But the tensor is a matrix. So you see it's a way of coupling together two vectors in such a way that the final vector is not always in exactly the same direction. And the word tensor is to do with this tension, it's to do with this behavior of mechanical behavior of objects. And actually in magnetic resonance then these tensors operate in the same way. They couple together vectors. So in this case the angular momentum of one spin is coupled to the angular momentum of another spin through a tensor.
Could you write the Zeeman interaction in the same way with a tensor coupling the two vectors?
Yeah, you could. In that case, it would be rather trivial. It would be Ij dot the unity tensor dot B, where the unity tensor would have a matrix which would just have ones on the diagonal and zeros everywhere else. But formally, it would be the same thing. Now I'll have to come back, we'll come back to just exactly how to fill in these dots in here. But let's just look at the overall mathematical structure first. The J coupling which goes through the electrons has the same form. But the form of the tensor is different, as we'll see in a minute. And the chemical shift since it involves the coupling from a nucleus through the electrons to the magnetic field, involves what's called a shielding tensor. And actually I just have to add the magnitude direct ratio in this case. But again, in general, the shielding tensor we can think of as a 3x3 matrix which couples together the magnetic field and the spin angular momentum. And it's possible to calculate these tensors using quantum mechanical calculations of the molecule. And it's very common to represent them. So if we have a molecular structure and we're interested in a nuclear spin at one particular site, it's very common to represent these tensors in the form of ellipsoids. Which are attached to the particular molecular site. So, if okay, I'm just going to run through. Back to that. So, for example, Lilia's program's finished represents these tensors in this way. And every tensor has three special directions called the principal axes. So let's look at this in a bit more detail. If you take this shielding tensor here, so suppose we have a molecule, and then one draws up an axis system. And then the magnetic field is applied along the z-axis. So this axis system I've drawn up there is called the laboratory frame. So actually in that laboratory frame, the magnetic field, Bx, with its three components, Bx, By, Bz, actually it just looks like 0, 0, B0. Because it doesn't have any X or Y components. That's just a choice of what the actual magnetic field is. The shielding tensor, in general, has 9 components, which one writes as XX, XY, XX, YX, YY, YZ, ZX, ZY, ZZ. So the chemical shift is then gamma J Ij is shielding tensor of the magnetic field. So we could expand that out if we wanted to into a whole set of terms, which would be Ijx, sigma XX, Bx, plus Ijy, sigma xy, By, and so on for 9 different terms. Now these, the tensor though is characterized by 3 special directions, which are going to give large axis labels to. These are called the principal axes of the tensor. And what does that mean? It means well, actually, let me back off a little bit. Before discussing that, let me just look at some let's look at the chemical shift. This is a sketch of the mechanism of the chemical shift, which is that when a molecule like this ring-shaped molecule here is placed in a magnetic field, the electrons start to circulate, and then circulating electrons themselves generate a magnetic field. So at the site of a particular nuclear spin, the magnetic field the nucleus sees is the sum of the external magnetic field and also this induced field. And note that the direction of the induced field is not necessarily in the same direction as the applied field. So that's why one needs a tensor to describe that relationship. Generally, it's in a different direction. And this leads to what's called chemical shift anisotropy. Here's a diagram of some molecules with different chemical shift tensors sketched in. Let me get that. Okay, this is more or less what I've just been writing on the board. Actually, I've been using delta instead of sigma. You can do either, they just differ with a change of sign. Let's not worry about that too much. Chemists tend to use delta, while physicists tend to use sigma. But the main point here is that a field is applied, and then the induced magnetic field, induced by the applied field through the electrons, is proportional to the applied field, but not in the same direction in general as through this chemical shift tensor. Okay? However, there are three special directions, the principal axes, in which so basically we have the applied magnetic field, we have a molecule, we have a particular nuclear site. The magnetic field induces currents in the electrons, which then act back on the nucleus. And in general, the induced field is not parallel to the applied field. However, if one rotates the magnetic field, so let's suppose suppose there's a chemical shift tensor attached to that particular molecular site. If one applies the magnetic field along the principal axis, then in that case the induced field is parallel. So in this particular molecular site here, there's a principal axis system which is represented by the directions of this ellipsoid. It has three principal axes, and those are the same as the principal axes of the chemical shift tensor. And if a magnetic field is applied along, in this case, this direction in the molecule, then the induced field seen by the site here is also in the same direction. So generally, if the magnetic field is applied at some other direction here, then the induced field might be off in a different direction. But for these special directions, the principal axes, the induced field is the same as the applied field, in the same direction as the applied field. So those three directions are a way of orienting the chemical shift tensor with respect to the molecule. So how does it go? So here I've written the tensor in the laboratory frame. So these axes here, the little eggs here, these are the directions in the laboratory frame. it's also possible to write the tensor in the principal axis frame. So PAS, or principal axis system. And in that frame, the tensor is very simple. It's diagonal. So what this is saying is that if a field is applied, so let's take a case, for example, where okay, so we have a molecule. We have a chemical shift tensor. But then we choose to write everything in the principal axis frame of the tensor. So the Hamiltonian looks exactly the same. It's just the way we write down the vector and the tensor is different now because we're using a different axis system. So if we apply a magnetic field, for example, then the components of the field along this principal axis, x-axis, would be called big X here. I have a feeling I'm making this a bit more confusing than I should, actually. Can somebody ask a question, please?
Yeah, that last bit about the magnetic
Yeah, so the idea here is that you can, suppose you have a vector B. You want to write it as three numbers. To write down the three numbers, though, you have to define which axis system you're using. So I suppose I have a magnetic field vertical. And then I use an axis system where x is here, y is here, and z is vertical. And the three numbers for the magnetic field are just 0, 0, B0, if B0 is the magnitude of the field. And that's because I use a laboratory frame in which the z-axis is along the magnetic field. Now I could equally well write the vector B in a different axis system. I could use the principal axis system of the chemical shift tensor, which might be some strange axis system there. And then the three numbers used here would be different. So I would take what I would do is I would take the the magnetic field and take the dot product with the x vector, for example, and that would become Bx, and the same for the y and the same for the z. So in the laboratory frame, B would look like that, but in the principal axis system, B would have three different numbers, which I could call B, big X, big Y, BZ. So there's like two choices here. In the laboratory frame, B, the magnetic field, is very simple. It's 2 zeros and then one number. But sigma is complicated. It's 9 numbers. In the principal axis system, B is complicated, it's 3 numbers, but sigma just has 3 numbers. And every interaction, each one of these interactions here has the form of a tensor and has 3 special directions called the principal axis system of that interaction. So, if we have a molecule and we have J, K, we're interested in the dipole-dipole coupling tensor, which was called DJK. Its z-axis is along the vector going from one nucleus to the other nucleus. So it's directly linked to molecular geometry. So the z vector, the z principal axis, is along the internuclear vector. And actually, it turns out not to matter which direction the x and the y are. For chemical shifts and protocol interactions, then they're also described by tensors. But the direction of the principal axes is something which depends on details of electronic structure. It can be predicted, but and there are some general rules for different chemical sites of different type. So for example, if you have a benzene ring, then the z-axis is usually perpendicular to the plane of the ring. But these are more detailed questions. So this would be the principal axis system for a chemical shift tensor. The main thing here is that to specify, I guess what I'm really trying to get across here, is to specify a spin interaction of this type, which is the type you always need in solids, and actually also in liquids if you're doing relaxation theory. you need to specify actually 3 numbers which are called the principal values. And also the direction of the principal axes. And in fact, you need 3 numbers to specify the direction of the principal axes as well. So what we want to do is to be able to write down and then put in a computer program to use for simulations these interaction terms, and then we have to specify these tensors. And to specify each tensor, one needs in general 3 numbers the principal values plus 3 angles which specify the directions of the principal axes. And software which does nuclear spin simulations, for example, requires you to specify in one way or another these the tensors, just specified in this way. And then there are various tools, different ways of calculating these, some of which are easy to use, some of which are difficult. But what I want to get at here is the idea that you need to specify these numbers, these 6 parameters, to specify each one of these tensors.
So do you take these principal values and then multiply them by the angles to move them into the... So you start with the anisotropic tensor, multiply it by the principal values to move it into the prospectus frame?
Yeah, so in the principal axis frame, the tensor looks like this, with a diagonal form with the 3 numbers along the diagonal. The only problem, though, is the principal axis frame is not actually oriented with the frame which you want to do the calculations, which is usually the laboratory frame. So you have to do a rotation which rotates from the principal axis frame to the laboratory frame. And I'll show you exactly how to do that probably next time. So we have so far then the general principle, though, that all the spin interactions are represented as the coupling between 2 vectors using a tensor. And then each tensor has a principal axis system and a set of principal values. And what we'll be doing is the mathematics to how that actually works out. Now, unless I'm mistaken, there's 1 more hour. Is that right? Is that how it goes this morning, usually? But I think what we'll do is have a 10-minute break. Okay. Okay, I'm conscious that I'm maybe not making this very easy to understand. But what I'd try, actually, it's a bit risky because I don't think I've actually done this before. So I want to try and just take a specific example, a simple example, and just try and work all the way through it to give you an idea. But it's risky, I might get it completely wrong. But what I want to do is what I'd like to do is take the chemical shift interaction from this one nucleus. I'm going to make a few assumptions just to make it an easy case. And calculate how the chemical shift changes as one rotates the sample. The key feature of all of these interactions we're talking about here is that they're anisotropic. They depend on the orientation of the sample. And I think this calculation would maybe give an impression of how this mathematics actually works. So I suppose I want to take a case which I think I'm reasonably confident about actually is chemically correct. So if you have a group like that, a ketone, where this is sort of coming out of the board and that's going in. And we're interested in the carbon-13 at this site here. Now, when the quantum chemistry people get to work on this, they can calculate the chemical shift tensor. And the chemical shift tensor would be represented as an ellipsoid, like this, with its z-axis, which by definition is the major axis, the biggest one, is perpendicular to the plane. That's just the way the electronic structure works out. So this is the principal axis system. Okay. So what that means is that if we write the shielding tensor in the principal axis system, then it's a matrix but with three components, x, y, z, z. And for simplicity, I'm going to assume, which is actually actually approximately true in practice, is that these two components, xx and yy, are the same. That's an approximation that is quite often close to being true. It depends on which chemical site we're talking about. But just to make the mathematics simpler, I'm just going to assume that. Okay. Now, suppose we have like a crystal. Suppose we have a single crystal which contains this material, with all molecules lined up in the same way. So I only need to worry about the orientation of a single molecule. Actually, in practice, most crystal structures have molecules stacked up in different orientations. It's not just a single orientation usually. But again, usually you have one molecule pointing that way and the next one like that. And there are very many complicated arrangements of molecules even within a single crystal. But for simplicity, assume just a single molecular orientation. And then we have our principal axis system like this. And now let's assume that the magnetic field is applied like this. And in general, there will be an angle between the magnetic field and the z-axis of the principal axis. We're going to call that beta. So the idea here is we're doing solid state NMR, so we have a single crystal in the NMR spectrometer, and we have some apparatus which lets us rotate the crystal and take the NMR spectrum as we rotate the crystal with respect to the magnetic field. And for each position we could calculate this angle beta between the principal axis system of the molecule. So as you rotate the crystal, the principal axis system rotates, and then the angle beta between the z-axis of the principal axis system and the magnetic field changes. What I want to do is calculate chemical shift based on this chemical shift tensor in the principal axis system. I want to calculate a chemical shift as a function of the orientation beta. So how does the chemical shift change as beta is changed? Okay. You following the problem here? So I just want to show how this mathematics works out, so maybe it's a bit more specific. So we have the Hamiltonian with this gamma, and then the angular momentum operator, the chemical shift tensor, and the magnetic field. And we have the chemical shift tensor in the principal axis system. It's just diagonal. Like that. And the magnetic field, expressed in the lab frame, just has one non-zero element. So I'm going to use these superscripts like that to denote which frame I'm writing a vector or a tensor in. And the problem is that the chemical shift tensor has a simple form, this simple diagonal form in its principal axis system. The magnetic field has a simple form with just two zeros and one number in the lab frame, but these two frames are different. So we have to do a transformation from one frame to another frame. So basically we have a principal axis frame with its axes here, and we have the laboratory frame with the magnetic field here in the laboratory frame, along the z-axis in the laboratory frame, the principal axis frame with the z-axis of the chemical shift tensor, which is actually the perpendicular to the molecular, the axis of the molecule, the perpendicular to the plane of the CO group, along the z-axis of the principal axis frame. And we need a matrix which transforms between these two frames. I'm going to call that matrix omega PL. R omega PL. It's a rotation matrix. In fact, when we get on next week, then I'm going to use this type of notation a lot. So this big omega PL is the relative orientation of two reference frames. So what this matrix would do is it takes an axis, a z-axis, if it's applied to the z-axis of the laboratory frame, the matrix will then convert it to the z-axis of the principal axis frame. And in this particular case, it can be written down in rather a simple way. In fact, in this case, it just depends on the angle theta. In general, actually, you need three angles here. I've chosen a simple case where we only need one angle. It will look something like this. So you might have to trust me a bit. Why does it look like that? Well, what I'm assuming here is that the principal axis frame looks like this, and the laboratory frame looks like this. I can think of an angle beta between them. So the y-axis I've chosen here, the idea is you take the y-axis and then rotate around the y-axis, and then the z-axis becomes cosine beta plus or minus x sine beta, which is what's being shown here. And similarly, the x-axis is rotated as well, giving cosine beta and sine beta here, while the y-axis stays where it is. Are you willing to swallow that?
So it's cosine beta and sine beta, cosine beta for z.
Yeah. So the idea here is that if I take the z vector for the principal axis frame and apply this rotation matrix to it, I should get the z vector for the laboratory frame. And the same for all the other axes. So So this type of thing is a rotation matrix for a rotation around one axis by one angle. You basically rotate a z vector here into the x component with the trigonometric functions cosine and sine, representing how far you rotate it.
Why does the y-axis stay in the same position?
It's just the actual rotation I've chosen here. You see, actually, there are many different rotations which rotate this vector an angle of beta away. But I've just chosen a simple one for convenience, in which I just rotate around the y-axis and keep the y-axis fixed. So since I'm rotating around the y-axis, it just stays there. It's just a particular choice here, actually. Okay, you have to trust me on this one. So the way the way the mathematics then works here is that I want to write the angular momentum. I want to write the angular momentum operators in the laboratory frame. I don't want to write it in this funny principal axis frame which is fixed to the molecule. And I want to write the magnetic field in the laboratory frame. Because that's where it's easiest to write. But I want to write the chemical shift tensor in its principal axis frame. So to get between them, I need to rotate I need to insert two rotations from the laboratory to the principal axis frame, from the principal axis frame back to the laboratory frame. And back again. You can see actually I need two opposite rotations. So the way this is going to go is I need Ix, Iy, Iz for the angular momentum operator in the laboratory frame. Then a rotation matrix. Then the chemical shift tensor. I'm going to use an abbreviation here. Then a rotation matrix back again. And then the magnetic field, where here C is cosine beta, S is sine beta. And actually I took the inverse of this matrix here by changing the sign of the sine terms. So then in principle, all one has to do now is calculate through what that is. So I haven't done this before, you can see. do a little bit of maths here now. So let's multiply these vectors out. So this times this would just give sine b0. This times this would give nothing. And this time this gives cos b0. Multiply these two together. This is not too bad. This just multiplies the x by this. X sine b0. This times this gives nothing. This times this gives z c b0. And now I have to multiply those together. This is going to be a little bit more meaty. I have actually I'm going to cheat a little bit. I'm going to only bother with this is going to give a vector, right? I'm multiplying matrix by vector. So I have 3 terms here. I'm only going to bother with the last one. I'll say why in a minute. So the last one is multiplying this row by this column. So that would be x sine squared b0 plus z cos squared b0. And then it's going to get multiplied by ix, iy, iz. I didn't calculate these, but they can have been multiplied by ix times something plus iy times something. And then the one I am going to bother with, which would be gamma iz x sine squared b0 plus z cos squared b0. Happy with that? And then again, I'm going to appeal to your trust by saying, I don't have to worry about this. They're what's called non-secular terms. Now what that is about is that this chemical shift interaction is not the only thing. We also have the very strong Zeeman interaction with the main magnetic field, as well as this chemical shift interaction. And that interaction is simply gamma iz b0. It involves iz, and these terms, ix and iy, they don't commute. They don't commute with the Zeeman term. Since ix and iy don't commute with the Zeeman term. This is called the secular approximation, and it's usually valid in high field NMR. So if we ignore these non-secular terms, which is usually valid approximation, then the chemical shift Hamiltonian is just this gamma. Let me translate it back again now. This is sigma xx sine beta squared plus sigma zz cos beta squared. So let's imagine what happens. So this actually is what we have here is the shielding factor for the spin as a function of beta. So let's imagine the NMR spectrum. And when we usually plot an NMR spectrum, the shielding scale increases from left to right. So what this is saying is that when beta is 0, and cosine beta is 1, sine beta is 0, so then we get the zz term. So that would be for beta is 0, which means that we have the plane of the molecule aligned perpendicular to the magnetic field. So if you remember, the principal axis system is perpendicular to the plane of the molecule. Now if we then rotate the crystal, then the chemical shifts change. So when we get the molecule perpendicular to the magnetic field, that would have beta is 90 degrees. And the chemical shift would now be XX, would be equal to the XX component. So basically the spectrum would be a single peak, but the position of the peak would change as one rotated the crystal between these two values, XX and ZZ. So one can imagine plotting how the chemical shift would vary as one changed beta. Actually, in the presentation I have here, this is an experimental example, which is maybe not wonderfully covered some data, but it's not on a single crystal, it's on a fibre, which also contains oriented molecules. But the molecular orientation isn't perfect, which is why the spectra are not so incredibly useful. But it's a silk fibre in which the protein which makes the silk has been labelled with N15. That's done by feeding the spider with N15 amino acids. So here's, so the fibre is actually an alpha helix. The protein forms an alpha helix. And you have these peptide bonds which have chemical shift tensors which are oriented in a specific direction with respect to the helix. So then by changing the direction of the, stretching the fibre, that orients the helices along the stretch direction. So you have the spider silk, and you stretch it. That orients the helices of the protein along the stretch direction. And now you've oriented the chemical shift tensors. And now you can put that in a magnetic field and now change the orientation of the stretched silk with respect to the magnetic field. And the NMR spectrum of the N15 changes. And it essentially changes to a good approximation exactly according to that formula there. So we have a peak which starts here and then moves across as you change the orientation of the fibre. Now, ideally you would like to see a single peak which moved over here and then back again. You don't see that, and that's because the orientation of the fibre and of the proteins within the fibre is not perfect. But it gives you an idea of the sort of thing which happened. Okay, so we have a sine squared term and we have a cosine squared term. The next thing I'd like, actually I'm really running out of time here. The next thing I'd like to do with this actually is to calculate what happens if you take the average of the chemical shift over all molecular orientations. So imagine that we now have this molecule, but it's in a liquid. So the molecule is tumbling around like crazy and experiencing every possible molecular orientation with equal probability. Now in a liquid then we get the average chemical shift averaged over all molecular orientations. So in other words, this beta angle here is not fixed anymore, but it's fluctuating around in the liquid. So let's calculate the average over all orientations. So this would be as what happens in solution NMR. Now, to take the average, you integrate over a probability distribution. So you have this angle beta, which is the angle between the z-axis of the principal axis system and the laboratory frame. And what we want to do is average over all values of beta. And beta can go from 0 to pi. So basically average this mechanical shift as a function of beta over all values of beta. But actually you have to be very careful here. It would be natural simply to take simply say, okay, the chemical shift varies according to beta like this. So I simply take the average value, which would be the integral divided by the range of beta. Actually, if you do that, you get the wrong answer. One must include the probability factor as well. And that arises because there's more ways of getting beta 90 degrees than there is of getting beta 0. Which sounds a bit crazy, but if you think about, well, let's say a mathematical argument is that the as you increase beta, then you have more possible directions around the z-axis, and the length of this line increases with sine beta as beta increases. So initially you only have a small range of orientations which gives a small value of beta, but as beta reaches 90 degrees you have a large range of orientations. So this weighting function here takes into account the probability of having a particular beta. And you know what, I'm going to leave that as an exercise. So this should be written as gamma B0 times the isotropic chemical shift. Sorry, I should have had IZ in here as well. It wasn't here. So the exercise is, what is the isotropic chemical shift in terms of XX and ZZ? So the idea here is that in a liquid, then one averages over all possible molecular orientations, and then one gets a particular isotropic chemical shift value, which is actually the average. Which is the average of the two values Now you would think that it's just halfway between this and this, but it's not actually. If you calculate this, do the integral here, you find it's not halfway between x and z. Any questions on that? You made me spin much now. Okay, so we'll leave it now and then we'll see if anything's